So today we will start looking at elastostatics in higher dimensions. So if you recall, we did elastostatics in 1D, right? But before going to higher dimensions, we started with the heat conduction problem because, well, heat conduction is let's say a friendlier problem, right? You go to higher dimensions while the field is still a scalar field. So you essentially, in the end, in the discretization, you're solving for 1 degree of freedom per node in the finite element formulation. So that makes things a bit simpler. But as you will see, most of the things that we did for the heat conduction in higher dimensions are going to still apply here. So from the variational form, when we set up the elastostatics problems in variational form, you will see that the natural boundary conditions are going to arise the same way that happened when we were looking at the heat conduction in higher dimensions. Okay, so let's get started. So you are already familiar to this setting, right? How we derive the discrete equations for any problem. Essentially, we set the problem, the boundary value problem, in strong form. We say, well, let's try to relax that requirement so that it is not satisfied at every point along our domain, but instead we try to satisfy that differential equation on average, right? And this is how we arrive to the variational form or the weak form. And then, well, I'm going to show you, and for those of you who took the nonlinear mechanics, you are already familiar with this lesson, right? So there is not going to be a lot of new information. We're going to show that there is really an equivalence between what we call the variational formulation and the principle of virtual work. So if you're coming from, let's say, a more civil engineering background, there is a lot of discussion on the principle of virtual work. What does that exactly mean? And in the end, it is essentially an equivalent statement of variational equilibrium, right? So the weak form, the variational form that is obtained by the method of weighted residuals, or the variational form that is obtained by minimizing potential energy, or the principle of virtual work, they are all equivalent statements of equilibrium on average, right? And then, of course, we looked at the Galerkin projection. We know that the moment we talk about variational formulations, we're still living in an infinite dimensional space, and then we say, well, now I want to adopt finite dimensional spaces, and in particular, we're going to adopt finite element spaces, and so we reduce the size of the problem so we can actually solve it in a computer. Again, for those of you who attended nonlinear mechanics, you are going to be quite familiar with what I'm going to discuss today. So, well, as we did in 1D, in 3 dimensions, we do the same, right? We set up equilibrium. So how do we do that? Well, we look at our boundary, right? Here we have our mechanics potato, right? We call that omega, as in the 1-dimensional case. So omega is essentially every point in our 2-dimensional or 3-dimensional domain. Of course, there are parts of the boundary. So here I have denoted gamma r, the part of the boundary with dropping boundary condition. And, well, it's kind of difficult to sketch that schematically. So I have basically just one point. But there is a region here with gamma d, where we're prescribing the Dirichlet boundary condition. So I'm prescribing the displacement field. And then there is a region gamma n where I'm prescribing tractions. And, well, you see that it's not actually only here, because in this region where I don't have anything, this is also a Newman boundary condition, right? So we just prescribe 0 traction there. And what I'm going to say is that at every point along this domain, right, I can define my normal vector. It's the outward normal unit vector that we define. So it's actually a field. And this is going to become important because at some point when we are going to apply the divergence theorem, of course, the idea is to transform an integral over a volume to an integral over the boundary, where our natural boundary conditions are going to show up. Okay? All right, so let's look at equilibrium. So if I take an infinitesimal volume of dimension dx, dy, dz, and I'm going to look at all the forces that are acting on that infinitesimal volume, you will see that, for instance, this force here is essentially sigma xx. So I'm denoting sigma xx as the component of the stress tensor that is perpendicular to this y-x plane, and that is also pointing in the x direction. And so to get that force, I multiply the stress, multiply by the area, and for that infinitesimal area, I'm looking at this portion of the infinitesimal domain. And of course, that has a different value than the one at this phase. So for this force, it's going to be sigma xx dy dz. And then I also look, of course, at all the other stresses that are acting on the other phases. So if I look at this phase here, of course, I have shear stress that is basically going to be sigma xy. And as you notice, this has a different value than the one that is in the back. So it's not really clearly seen here, but here you have sigma xy on the back phase. And I do the same with the other shear stress, right? So these two. And so in addition to all that, so those are essentially the forces that are acting on the faces of the infinitesimal cube due to the stress tensor. Keep in mind that, of course, we can make this infinitesimal cube as small as we want, still with some variation, because that is what is going to lead us to the differential equation that we're going to solve. And then, well, we have this force that is bx dx dy dz, and it's a volumetric force. Normally, we talk about it as the body force. And when we talk about body force, we're normally thinking about well, your weight, right? The weight of the body. So in the case of the weight, this is going to have a component just in the direction of the z e3 vector. And so when we write down equilibrium, and again, it's a static equilibrium, so we're not looking at dynamics in this course. If it were dynamics, then you would have all that equation equal to the mass times the acceleration in the x direction. But since it is a static equilibrium, all this has to be equal to 0. So if you see, I have, again, these two parts are the difference in the force in the x direction due to the sigma xx component of the stress tensor. And then this is one of the shear components and the other shear component, and then finally the body force. And then, well, if we divide by the volume, right, and we take the limit as that infinitesimal volume goes to 0, we get basically the definition of the derivatives. And in this case, we're dealing now with partial derivatives as opposed to in the one-dimensional case, we were dealing with the total derivative. Now we have partial derivatives, okay? And so this is the equation of equilibrium in the x direction, right? But of course, we're dealing with a two-dimensional or three-dimensional problem. And so we're going to have either 2 or 3 equations. And so you can vary, yeah? Yeah.
In the cube, it has the notation sigma x z, but then in the equation it is sigma zx.
Well, the stress tensor is symmetric, right? Yeah. So that is the result of the balance of angular momentum. Indeed, I should have kept it the same way as in the cube, but it doesn't really matter because we know that the stress tensor is symmetric. Okay. All right. So now that we know the differential equation, if you recall, that is not the only thing that we need to set up the boundary value problem. We need the differential equation and the boundary conditions. So we can very compactly write the differential equation in this way. You have all seen this equation, the divergence of the stress plus the body force is equal to 0. And notice that I have a 0 vector here, right? Because we have how many equations? 2 or 3. Right? We're in higher dimensions now. And then the boundary conditions, as we described, well, we have a prescribed essential or directly boundary conditions. We're prescribing the displacement field in some part of the domain that we call gamma d, right? We have a prescribed traction, and this is the so-called Cauchy's relation, right? That relates the state of stress with the tractions along the boundary. It's called Cauchy's relation, right? So essentially, if at any point along the boundary, I take the stress field, and I basically multiply that by the scalar. Remember that the stress was a what order tensor? Stress is a second order tensor, right? So if I apply a second order tensor to a vector, do I get what do I get? A second order tensor applied to a first order tensor yields a first order tensor, so we get a vector back, and that's our traction, okay? That, of course, applied to gamma n. And finally, if you recall, once again, we have looked at this many times, so by now it should be very, very crystal clear to all of you that we have a Robin boundary condition that is supposed to be kind of a mix between the two, right? And as I increase the values inside this tensor, that now is going to be a d-dimensional tensor, right? Because I can assume that the stiffness that I place into this spring, right, could have different values depending on the direction that I'm looking at. So I'm thinking of this as a d-dimensional tensor, right? And so as I increase the value of the components of that tensor, then of course I'm going to make a directly boundary condition, right? It's like if I apply a displacement here and this is very stiff, well, the same displacement is going to be applied at that point, okay? Okay, well, the rest that you see here is just notation, essentially the function, basically domain, codomain. So if I look at the stress, Cauchy stress, the domain is a closure of omega, and I'm just saying that it's just a d-dimensional second order tensor, right? The body force is just a vector, the same with the prescribed displacement, the prescribed traction, and again, this H is some sort of elastic support, as we discussed, and I have also as a tensor, it could be it could also be, let's say, a scalar multiplied by the identity matrix, for instance, and in that case, you give the same, let's say, the same spring constant to all directions. All right. Again, strong form. Now we go to the weak form, right? We say, well, let's make sure that now we set up the problem in such a way that we relax. The idea is that we relax the requirement, and that has to be satisfied point-wise in our mechanics potato, and then we do the same thing we have been doing in this course from the very beginning. We take our differential equation, we use the method of weighted residuals, right? So I take the differential equation, I do the dot product with a test function. Now we are dealing with vector-valued functions, right? So this is a vector, and each component of that vector is a function. That's why it's called vector-valued functions, okay? And notice that I do the dot product between these two. So the differential equation was either a two-dimensional or three-dimensional vector. And then this is also going to be a two-dimensional or a three-dimensional vector. So the dot product between those two gives me a scalar. And therefore, if you notice, I put here 0 scalar, not a vector, right? So when I do this and I integrate over the domain and I set that equal to 0 for all vector-valued test functions in some space, right? Then again, I am setting my projection, right? So then, as you all know by now, what this is going to, it's going to yield the best possible solution U inside that sigma, because U, of course, is hidden inside sigma. Remember that sigma is a function of strain, and strain is a function of our displacement field, right? So that this projection holds, right? The idea that I am saying that this orthogonality condition has to hold, then eventually is going to result into finding the best U that makes that happen. And that is the great thing about the Galerkin projection and the, well, Say's approximation theorem, as you probably read already in the notes in the book. There is a strong proof that that is the case. All right. As in the heat conduction problem, we're going to apply an identity, right? So here I wrote that this term here, right, is equal to all that. And, well, I prove it at the bottom. But for the time being, I am not going to say anything about the symmetry of the stress tensor. So I'm not going to use that property. We know that that holds. Again, that is the result of the balance of angular momentum, right? If I have, let's say, static equilibrium, I know that the result of angular momentum says that the cross components of the stress tensor have to be equal, so the stress tensor is symmetric, but I'm not going to use that property. I'm just going to keep that sigma t for the time being, because as you will see later, I'm not going to need to use that property, right? So just a very quick consistency check. When you see something like this, right, you have to see, well, let's say I have the stress tensor. The stress tensor is a rank? It's a second order second order rank tensor, right? Then when I take the divergence of that, I get a first order. So I get a vector, and then when I do the dot product with another vector, I get a scalar. So this whole thing on the left is a scalar, okay? Now, this is a vector. Now, if I apply the divergence, the stress tensor applied, again, the transpose of the stress tensor applied to a vector gives me a vector. And then if I take the divergence of a vector, it gives me a scalar. So far we have scalar here and scalar here. And this, what you see here, is essentially a second order tensor, and the gradient of W is a vector, the gradient of W is a tensor. And what you see here is a contraction operator. So basically, if you have two second order tensors, right, and you see this symbol, that is essentially it's like a dot product between second order tensors. So you go to the first component of your first tensor, right, the 1, 1 component of the first tensor, you multiply by the 1, 1 component of the second tensor, plus the 1, 2 component times the 1, 2 component, plus, and then you do it like that. So again, here you also have a scalar. All right, so this is so-called contraction operator. So when you replace that identity in the formulation, you see that, well, this term here is going to become this whole on the right. And so you see that if I look at this term, right, we again are going to apply the divergence theorem or Gauss theorem. And the idea is that we transform that integral over the volume, we transform it in an integral over the entire boundary. So how do we do that? Well, we take what the divergence is being applied on, and then we multiply that by the normal, and that is essentially the result. That is just a result of the divergence theorem. And there are actually different flavors of the divergence theorem, but this is the one that we choose for this. And notice that by definition of the transpose of a tensor, I can swap these two guys here. I can swap them. This is just by the definition. So the operation of the transpose of a tensor is defined so that this operation holds. We define it that way. Okay? So as you see in the end, if I can swap these two, right? Suddenly here I have what? What is this? That's our boundary condition. So our natural boundary condition, again, nicely, magically arises in the formulation by simply applying the divergence theorem, right? Now, of course, remember again that this is an integral over the entire boundary, but our boundary is comprised of how many boundaries? 3 boundaries, right? We have our Robin, our Newman, and our Dirichlet boundaries, and so we are going to split that integral into three integrals because we know that those domains are disjoint, right? So they don't overlap. And so this guy here is going to be translated into a portion that where we're prescribing the Newman boundary condition, one that we're prescribing the Dirichlet boundary condition, and one the Robin boundary condition. And as you see, I already say that this guy is going to be equal to 0. Again, the same thing we did in the 1D case, the same thing we did in the case of heat conduction. Why is that? We don't have to think about it, right? We just say, well, let's make our life easy. Let's make sure that our test functions are going to be 0, right? We don't have to deal with the reaction term anymore, which is this guy here, the reactive traction in this case, right? We don't have to deal with that. And so the variational formulation, again, by following the method, the so-called method of weighted residuals, which I think is really the most, in a way, the most general way to get to your variational form. And I say that because, well, there are some equations that cannot be derived from a potential, but you can always apply the method of weighted residuals. So again, our weaker variational form is stated always the same way. We state it in abstract form. We say find U that is, of course, part of some space V0. And again, recall that we're dealing with vector valued function spaces now, right? So now, what that means is that every component of those vectors that we're going to choose, right, belong to a Sobolev space of some order. In the cases that we deal in this course, those are going to be in H1, as we discussed at some point, right? For some other problems, they may be in a different high order space. But again, we're always dealing with Sobolev spaces because if you recall, we require not only the functions that be square integrable, but also their derivatives in the domain of integration, all right? And so in abstract form, we write it the same way, find u such that the bilinear form is equal to the linear form for all vector value test functions in that same space, right? And so for this particular case, where we're considering also the Robin boundary condition, our bilinear form is not only comprised of the part that is the internal strain energy, but also the part that arises, the unknown part of the Robin boundary condition that arises, right? So remember that the Robin boundary condition had two parts, one that you don't know, which is this one, and one that you knew, which is this one. And the linear form, you have the body force term. We didn't touch it, right? We just left it like this all the way through. And then you have your Newman boundary condition, and again, the Robin boundary condition, the known part. And so, well, with this, now we are ready to go for a discrete formulation. But before that, I want to show you the equivalence with the principle of virtual work. Because if you look at this, right, this expression, well, I know that this term here has to deal with the internal energy, right? We know that. And so in the principle of virtual work, we see that maybe this guy here is related to some sort of strain, right? So the gradient of W is maybe perhaps too mathematical, but maybe we can cast this in a different form that is more familiar to us, right? And so for simplicity, we assume that there is no Robin boundary condition. And if I now use the property that we know from the stress tensor, which is that the stress tensor is symmetric, I can write that this expression here can be written as the symmetric part of this guy, which is defined like this. The symmetric part of that tensor is defined as 1/2 of grad W plus grad W transpose. It is defined. That is what we call the symmetric part of a tensor. And so that very much looks as our linearized strain, right? But it is not really our actual strain because I'm not using the function u here. It's not the displacement field, it's the test function. So it is not actually our actual strain, but you could see it as some sort of virtual strain, right? And so if I define this guy here as delta epsilon, and I just change the notation from W to delta U, our variational displacement or our virtual displacement, then just replacing back in the previous expression gives us an expression that is way more familiar to us. So as you see here, you have this term here. Remember that I got rid of all the Robin boundary conditions for simplicity. So now our statement of variational equilibrium is simpler, right? But here you see that now we have essentially what we already know and we are familiar with, which is the principle of virtual work, right? So this guy here is going to be our virtual strain, and everything that you see on the right-hand side of this expression is essentially the work done by external forces, right? And obviously, you don't see an expression for all test functions or all virtual strains in some space, right? We never talk about that when we deal with the principle of virtual work, but you probably heard for all sufficiently smooth functions that satisfy the boundary conditions a priori, right? That are smooth enough. Like you hear this type of statements that are in essence equivalent to for all test functions in a given space, and we define what are the characteristics of the functions in that space, right? But again, this is just to show you that both formulations are equivalent, right? The statement or the principle of virtual work is an equivalent statement of equilibrium as that we obtain by just simply applying the method of weighted residuals. All right, time to discretize. So now that we have our variational form, we just go to a finite dimensional space. And for that, we use finite elements. So we discretize our domain, and you see that I subdivided here my body with all these triangles, non-overlapping triangles. And when someone asks you, what do you actually discretize in the finite element method, you should always reply the equation. We don't discretize our domain. We discretize always the equations, right? And it just happens that it may seem as if we are discretizing the domain. That is just the case in the HFEM, right? There are more advanced formulations where we can have, for instance, overlapping domains, and so we are still discretizing the equations, okay? So to get to the Galerkin projection, we are just going to replace UH. So everywhere you saw U, now we have a UH. Again, H is the symbol that we use to denote the mesh size. So essentially, in this particular case, I would define as H as some sort of diameter of a circumscribing circle for the biggest element, right? Because remember that in HFEM, the error in the end is going to be controlled by the smallest element or the largest element? The largest element. And we're going to talk about that in 2 lectures from now, right? Convergence. We're going to look at that. So our statement, as you see here, is the same. I just have replaced U by UH and W by WH. And so what are we going to choose? Well, let's look at some functions. So every single element here is going to be comprised of 3 functions. So I have triangles. Those are linear triangles, the so-called constant strain triangle. And though I'm not going to show you yet the functions, we're going to look at that in the next lecture, where we're going to be talking about isoparametric formulations. For now, notice that every triangle is going to have 3 functions, and those 3 functions are going to be mapped from a canonical element, from a master element. And so I can write the entire displacement field in this form, right? Where phi I is the so-called Lagrange shape functions that is associated to node I. So if I have n nodes in my finite element mesh, I'm going to have n shape functions, right? For instance, if I take this guy here, this node, well, the shape function that is associated with that node is going to be equal to 1 at that location, and it's going to ramp that down to 0 along all those edges, right? That is, so you can think of it some sort of pyramid, in this case with 5 edges along the base, right? That is going to be the shape function associated with that node. And again, just because that function is equal to 0 everywhere else except for this area here, we say that this area here is essentially our support for that shape function. Okay, so we can write the now is so-called trial solution, right? Because now, again, we are moving away from infinite dimensions, so now we call it trial solution. So this is a solution that we're going to try to see how it works, if it is good enough or not, right? And we accept that there is going to be some error. If we write the test functions or the vector value test functions in the same way, again, we are applying the so-called, who recalls, there were 2 versions of the Galerkin projection. If you take both the trial solution and the test functions from the same space, no. Who recalls this? You had 2 different versions of the Galerkin projection. One where you were taking both the trial solution and the test function from the same space, and the other one where they were taking from different spaces. Petrov-Galerkin is the one where you're taking from different spaces. So this one is called Bubnov-Galerkin. Very good. So I express both the same way. And so when I just plug back this one here and this one here, and of course this one also here, then you get the discretized version for this problem. And this U, right? If you see, U is the so-called degree of freedom vector. Very well. And only in this particular case where our shape functions are fulfilling these nice properties, so-called Kronecker delta properties and partition of unity properties, this is also called the displacement vector. But only in that case, okay? As I already told you multiple times, when we move to other formulations, like for instance, in particular, PFEM in this course, you will see that we cannot call that the displacement vector because, of course, there are degrees of freedom that have nothing to do with the displacement. They are more related to the derivatives of the displacement. Okay, so this U is the so-called degree of freedom vector. Of course, I can represent all the vector functions, the shape functions in that discretization with a huge matrix that you can see here. This is uppercase phi. Also recall that when we use uppercase symbols, we're thinking about global quantities, right? When we're thinking about lowercase symbols, we're looking at one element, okay? And so we are going to use the so-called Voigt notation, right? So in essence, Voigt notation gives us a way to reduce the dimensionality of our tensors for computation, right? If you recall, this is a fourth order tensor, right? The constitutive matrix is a fourth order tensor that is relating to second order tensors, right? But when we are writing code, we really don't like working with fourth order tensors, right? We normally work with matrices. And even though second order tensors are not matrices, right? Never think of them as matrices, right? They can be represented in the same way. Remember that a second order tensor is an object that operates on a first order tensor to yield a first order tensor, right? Mathematically, we can express them as matrices, but they are not matrices, okay? They are objects. Different way of thinking, all right? So because we don't like dealing with fourth order tensors, we are going to use the so-called Voigt notation, and we're going to take advantage of the symmetries of this fourth order tensor to reduce the dimensionality of our tensors. So what do we do? Well, the C has 81 components, but there are only 21 components that are independent due to symmetries. And so this allows us to write my stress tensor simply by a one-dimensional vector, and the same with the strain, right? As long as this quantity holds. So if you recall, stress contracted with strain gives me some sort of energy, right? So as long as that quantity holds, right, then I can do this. And to make that hold, this is what I need to do. I need to express gamma as the sum of two things, right? Otherwise, this does not hold. Why? Well, because a second order tensor in 2D has how many components? No, 4. In 2D it has 4. And how many components do I have here in the vector? 3, right? And so how do you make sure that your energy remains the same? Well, you have to account for twice the shear strain. And so in 3D, you apply the same trick. So this is the way we write our second order tensors. We reduce the dimensionality. And now my C matrix, right, I am going to write it also as a second order tensor, right? And so now I can do that. Well, the strain displacement matrix for this case, if you recall, that was essentially the matrix that we are going to be using to relate strains and displacements, right? And in the case of 2D elasticity and 3D elasticity, we obtain that matrix by simply applying this differential operator to our shape functions. And in 2 dimensions, it has this form so that we can use Voigt notation. Remember that we're dealing with 3-dimensional vectors, right? So if I want to apply, let's say, my stress, I want to obtain my stress by applying some sort of operation into the strain. My strain is a 3-dimensional, sorry, it's a vector of 3 components. Well, this has to have also 3 components, right? And so these are my 2 differential operators in higher dimensions, right? This is very different from what you have in the code. We discussed this briefly last time, right? When we met, we said this is normally the way you will find it, the way your strain displacement matrix is computed. But obviously, this is very dependent on 2D or 3D elasticity. Notice that if I want to implement this formulation for 2D elasticity, I have to use this version of my differential operator. If I want to do that with 3D elasticity, I have to apply this. Well, in the code that you have, we have a more general formulation, right? That you can apply to 2D or to 3D regardless. It's the same code, right? So these operations are implicit into the so-called symmetrizer operation that you can also see by yourselves in the code. Okay? All right. So this is finally the shape that is going to take our strain displacement matrix. And notice that all of these guys are a function of physical coordinates. And that is what we need. Always our strain displacement matrix is a function of physical coordinates. But as you know, all our shape functions are in parametric space. They are all defined in a triangle, right, that lives in my canonical element because all my integration rules are defined in that canonical element. The triangle is basically having 0, 0 as the first coordinate, 1, 0 the second coordinate, and 0, 1 the third coordinate. So that is my canonical element. And because the derivatives in this matrix are a function of physical coordinates, you already understand that there has to be some sort of Jacobian transformation that has to be applied so that I can actually obtain this matrix. Okay? So if you recall in the code, the first thing that we do at every Gauss point, we obtain the shape functions and the derivatives with respect to the master coordinate. So in order to get the derivatives with respect to the physical coordinate, this is where your inverse of the Jacobian matrix jumps in. That helps us basically taking care of this transformation. All right? Okay, so void notation, these things get much simpler now because now we're no longer dealing with 4-dimensional constitutive tensors. Now our constitutive tensor is going to become a 2-dimensional rank tensor. And well, if you write all that at the element level, right, remember that we had two ways to get into our discrete set of equations. One way is like, okay, we take our Galerkin projection, we just plug in our trial solution and our test functions, and you can write in component each equation, and that yields in the end your complete system of equations, Ku equals F. Well, we can also look at equilibrium at every element, right? And then you can obtain the global equilibrium as an assembly of the contributions of all those elements. So if I do that here for one element, you see that this term here leads to the so-called stiffness matrix at the element level. This is my local stiffness matrix. And this whole thing that you have here gives me the so-called local force vector. This is my local force vector, right? Where you see both the contribution of my body force and also the effect of the traction. So this should be a prescribed traction here. So it should be like this, right? And so in the case that it just happens that the boundary of that element overlaps with my Newman boundary condition, well, I have to take care of that. Yeah? If not, I don't have to take care of that. So how do you implement this? Do we actually go element by element and then we see whether the element overlaps? And then we go crazy, right? We don't do it like that. So normally when you prescribe a Newman boundary condition, you know the part of the boundary where you're going to prescribe it. So you basically get the edges of those elements and you just perform integration in those elements. Okay? Okay. The only thing remaining is how this is defined. And in 2D plane stress or 2D plane strain, they look like this. So again, E is your Young's modulus, Nu is your Poisson ratio, this is your identity matrix, and this is a unitary matrix. So basically every element in that matrix is equal to 1. And well, these are 3x3 tensors. In the code that we have, right, because we have changed the way things work, so it's more general, my constitutive matrix is a 4x4 matrix. So I want to emphasize this because at some point you're going to be dealing with the code and you're not going to understand where these things are coming from. Where it is because we have a more general code, but things are written differently. But at the same time, they both produce the same local stiffness matrix. Yeah? Okay, this is in 2D. When we go to 3D, now it looks like this. This is our constitutive matrix. This is a 6 by 6 matrix. But again, when I compute these local quantities, we always have to think about the dimensions of the things that we use, right? So for instance, if I have a 3-noded triangle in 2D, my stiffness matrix is going to be how big? Well, let's think about it. How many degrees of freedom per node I have in 2D? 2. How many nodes do I have? 3. So then my stiffness matrix should be 6 by 6, right? So somehow I have to multiply. I'm in 2D, so I'm basically dealing with these matrices, right? These matrices are, sorry? No, in this particular case, they are 3 by 3. 4 by 4 in the code, okay? But here, 3 by 3. So somehow I have to multiply B transpose CB so that I get a 6 by 6 matrix, right? So if this is 3 by 3, then B transpose has to be of which size? 6 by 3. And B? 3 by 6. So now I have 6 by 3 multiplied by 3 by 3 multiplied by 3 by 6 gives me a 6 by 6 matrix. And indeed, the way we have defined that B matrix, right? You notice that this is for the first node, this is for the second node, and let's remove this guy here and let's say this is for the third node, right? So indeed, you have a 3 by 6 matrix, okay? Yeah?
On the next slide,
Yeah?
where the plane stress and plane strain matrix, what's the weird one?
Sorry?
The weird one.
The weird one?
Like in the, for example, 2D plane stress.
Yeah?
Second term of the 1-1 element.
This one.
Yeah.
This is a unitary matrix. So every element is equal to 1, as opposed to identity matrix where only the diagonal terms are equal to 1. Yeah? Okay. So again, we obtain the discrete equations by just assembling the contribution of all the elements, right? And then we obtain our system, Ku equals F. Same thing we did in the 1D case. Everything we learned in the one-dimensional case translates nicely and smoothly to the high-dimensional case. The only difference is that, well, now we had to apply some sort of identity and then apply the divergence theorem, right? And to make sure that we're dealing with consistent quantities, because now we are dealing in higher dimensions. So the fact that we're dealing with vectors and tensors makes everything a little bit more complicated, but overall, it's exactly the same thing, right? All right. That's it for today. Are there any questions?
Can we maybe stay here after the lecture?
Yes, of course you can stay.
Yes.
We'll talk about it. Any other questions? All right. The next lecture, we're going to look at isoparametric formulation, and then we're going to delve in the world of PFEM. Yeah?